Good evening, everyone, and welcome to episode 6 of the Explorer series Real World Firebase Data Modeling. To introduce our panel today, we have our very own Samira Piyadigamage, who is a senior technical lead over here at Capstars, and Sukita Jasinger, who is our principal engineer. They will be joined by Chamindu Munasinghe, who is the CTO of Azen Technologies. And today they will be taking you through the ins and outs of FASTO, its data structures, through the means of a sample problem and their gamut of solutions. As always, we will be hosting a live Q&A at the end of our session, so do feel free to drop your questions into the chat box and we will take them up later. So without further ado, we'll get started. Over to you, Samira.
This is more of a explanation of how we design real-time real data models into Firebase, maybe from relational to NoSQL databases. After that, we'll be going into discussing Firestore benefits and limitations and trade-offs. As the last resort, we'll be showing you a demo application that we have built with use of Firebase, authentication, cloud functions, and Firestore database. You may be wondering why Firebase, why Firestore? Why not MongoDB? Because MongoDB is also a NoSQL document sort of database. The real and the main reason for us to go for Firestore is that the simplicity of it. And to be totally honest, the other reason is that real-time data streaming, that you will feel that you actually in bond of like real interaction with the application, because whenever something updated, it's get notified. For example, like Facebook, whenever someone liked your comment or something, you'll see the real-time notification. Like with Firestore database, achieving this would be a breeze. It's really easy. And another reason is for us to go for Firestore is that unlike in MongoDB, it supports transactions. So the as a last point on why Firestore is that it supports offline database out of the box, because if you go with MongoDB having to have offline database support is something that you have to write by yourself. But with Firestore, they support out of the box, meaning that whenever you disconnect from the internet, your data that has been already cached will be available to you through the application, as well as whenever you create something, will be get created on the mobile device or the web app. And whenever the connection got restored, it will be synced back to the actual database, and it will be available throughout the application environment. So we have a demo. We have also a demo ready for you to showcase what we can do with Firebase and how we should be doing it, and we'll be walking you through the demo at the end of the session. And we are expecting you to have a basic understanding of Firebase and Firestore in general, as we'll not be doing an initial setup there. So to summarize a little bit about the usage of Firestore that we have done in our real scenarios, that we'll be using Firestore for a few years now. There are applications we've built ranging from 10 users to million users built on Firebase services. So far, we do not see any performance issues. I think the main reason is that we have used it correctly. We have modeled it correctly. That way, we can cater for million users easily, because the way that we modeled the database was correct. So that's what we are going to tell you today how we did it. So let me introduce you to Chamidu, where he'll be taking you through the differences between Firestore databases and traditional SQL and NoSQL databases. Over to you, Chamidu.
Hello. Hi guys. I'm Chamindu, and thank you, Samira, for that wonderful introduction. So now, from the beginning of the history of computing, we use databases, right? So there are different types of databases throughout the history, right? So mostly we are using relational databases. So basically, with relational databases, I'm sure everybody who's here today have worked with a relational database, right? So we store data as relations, right? Normalized data in tables. So basically, this is a very familiar approach to everyone, and it's easy, right? But the problem is with uh, relational databases, how do you scale, right? You can always scale up, right? Or what you call vertical scaling, where you can, see with the increased load, with the increased number of users, increased database activity, we add more resources. Let's say, for example, if it's computation intensive, we might add CPUs or RAM, or add more network bandwidth, right? But the problem is when you scale up, you are going to hit a ceiling, as well as going up is going to be very expensive, right? But, but is there a way for us to scale out, scale horizontally? But the problem with scaling databases is, databases are use shared state, right? So, when we develop web applications, we are discussing about shared nothing architecture. But when we do databases, the state has to be shared, right? So, and traditionally, when we design applications, our consistency boundary is enforced by the database. I mean, if I may explain that more in detail, right? If you want to do transactional operations, right, that is handled by the database, right? Databases, almost all relational databases have ability to do atomic transactions, right? So we study about the acid properties when we study database systems. So atomicity, consistency, isolation, and durability. So I'm not going to go into details about these concepts, but I'm sure most of you are aware of those concepts, right? So basically, now how do we scale out or scale horizontally, right? With traditional databases, of course, I mean, there are ways to scale out, right? That if you take any enterprise level database like Postgres, Oracle, or SQL Server, you can scale out different nodes. But the problem there is your data write operations will not complete until all the nodes are synchronized, until all the nodes are consistent, right? Now, traditionally, SQL database clusters are like 2, 3, or maximum like 5 nodes, right? So we can live with that. But imagine if you have to scale out 100 nodes, if you have to wait block until all the 100 nodes are synchronized, that is going to be a nightmare scenario. So because of that, we have to give up on that strong consistency model, right? So most of these NoSQL databases achieve almost infinite horizontal scalability by giving up on consistency. But in reality, we can't totally give up consistency because our data has to be consistent eventually. So basically, that's hence that we are introduced to this term called eventual consistency, right? So basically, now almost like all these NoSQL databases, you can scale out, right, easily by sacrificing some consistency, right? So basically, I mean, again, like if you want to study about the theoretical aspects of this, there's this concept called the cap theorem, right? Where you have to choose between consistency, availability, and partition tolerance, right? Any database system will prioritize one of these two, one of the three, one or two of these three concepts, right? So now, yeah. So basically, when you take applications, right, almost all the applications, we are almost always reading data instead of writing, right? I mean, depending on the application, for 1,000 reads, you might have one write. Right? So it makes sense to optimize on the read side, right? So instead of like writes, even if writes take a long time, I mean, not a long time, we can live with that, right? So, and the other thing is, databases like Firestore or MongoDB, they don't rely on the relational model, right? So there you don't have joins, like there's no SQL, right? There are no SQL databases, right? And because of that, we are expected to denormalize our data, right? Because otherwise, if you try to use a normalized model on a NoSQL database, the performance would be unacceptable, right? It will be very inefficient. So basically now, and also one thing that I have to mention here is that it's always a trade-off, right? In anything, anything in life, it's always going to be a trade-off, right? There are no silver bullets. So there's always a trade-off when you go with, when you choose one product or technology over another, right? So with NoSQL, throughout my career of like 20 years, I have seen a lot of teams adopting NoSQL databases and failing because, like there's this saying, like, I mean, I think it's partly responsible for this is like for these failures is the database companies themselves, right? They advertise the databases, like, for example, like MongoDB has, you don't have to worry about the schema, right? They are schema-less, right? You don't have to worry about the model, just dump the data and you can tune it later, right? But that is not the case because I have seen in the real world, because of bad data modeling, there's a lot of there are cases where some of the use cases cannot be satisfied because the data is so normalized. Some updates take very long, right? So I think this session will help you guys to understand how to model data in the using NoSQL databases. I think the knowledge you gain here will be not only applicable to Firestore, also some of this knowledge can be applicable to other databases like MongoDB, right? Or maybe DynamoDB. Right? So yeah, with that I hand over back to Sukita, right, to carry on.
Thank you, Chamidu. Hope I'm audible. Yeah, great. Okay, so it was like a really comprehensive comparison between SQL and NoSQL. So let's go detail into Firestore data structure. So as both speakers discussed, Firestore is NoSQL document-oriented database. So unlike SQL databases, there are no tables, rows, columns, and specially relationships like foreign key constraints. So that's the trade-off Chamidu talked about. So we are going to use databases without joins or without foreign key constraint, which the application has to build the way to support all these things. So that's where where we focus on this session. So basically, if you take the Firestore data structure, it is like it's hierarchical. So you have collections, which has like similar type of documents, And then each of these document could have sub-collection associated it. So then there could be documents inside the sub-collection which associated with another sub-collection. So the structure keep going. So that's the basically how data structure arranged in Firestore. So these documents are JSON documents. So JSON documents contains keys and values. So these key value pairs, value could be like different types. Like I have mentioned here some of them: integer, floating point number, text string, Boolean, map, array. So map and array are like two special kind of structures, where map we can consider as partial document. So it also could have like key and values. These values again could have the same types. So you can go through the Firestore documentation and you can see all these types. And we are not going to talk much about that. And then, yeah, we talked about the sub collection and then maps as well. So yeah, let's go into the next slide where we discuss more about Firestore querying. So relational database has relationships, so they allow join queries to run top of that, and which is like flexible, but which lead into poor performance in queries in poorly modeled databases. But the NoSQL databases like Firestore has reduced that by providing by making all the fields indexed. So that's some conscious decision they had made. And if you talk more about the querying, these queries we call shallow queries. So if you run a query on top of collection, then you get only the document. You won't get the sub collection associated with that particular document. So you have to make sure that your document is fit into your view. So basically when we talking about Firestore, we're talking about app building. So you can take this as thumb of rule. Your document should fit the view. That means, like, let's say, in order you to render a view, if you have to go and query multiple times and get like hundreds of documents, then it's poor in user experience, and then you pay more for this querying as well. So you have to make sure that your document is fit. If you have like very big document, that means like multiple clients could come and try to write or read on same document, which eventually could fail. So there are like ways to prevent that, but still we should prevent happening that. So make sure that you fit the document size. And other thing is, you can run only on specific collection or sub collection. If you don't have like specially go and created collection group indexes in Firestore. And let's discuss how Firestore query scalability works. So Firestore has taken a conscious decision, as I mentioned earlier, to index all the fields. So they, rather than letting developer to go and select and create their indexes, then this allow front-end and app developers to adopt the platform very easily and jump in and quickly start building the application. So Firebase not only index the fields inside the document, but also fields inside the maps, which inside the documents also get indexed. And also objects inside the arrays also get converted into maps and indexed and stored. So it's really easy you to go and start writing your application, because all the fields are now indexed, so you can query by any field. So because of that, there's a trade-off. The writing is really slow. It's not really slow, but compared to read, it's really slow, but read is really fast. So Firestore read performance not depend on the number of documents in the collection. That means like if you have 10, 100 or million, still the read performance of the query is the same. So that's how they have achieved the query performance. And then let's go to the next slide. And if you take, as already Chabidu mentioned this, so when you build application, most of the time reads are much higher than writes. So because of that, we have to focus on the read access pattern. So when you go and design a NoSQL database, the first thing is you have to write down all your access patterns. Then the model based on your access pattern. So focus on the query, focus on the access pattern, and model the database according to that. So there's downside of this is you need good understanding about the domain when you're doing the design. Okay, there are two types of main queries you'll be able to run. One is indexing queries, other one is composite indexing queries. So in indexing queries, there are again two types of queries you can run on Firestore. One is like value compare, like equal or not equal. Other one is range query, less than, greater than, less than or equal, or greater than or equal, kind of. So there are two special operation you could run. Array contains any. If you have any array field, then you could run this type of queries on this operation on top of that. And then you don't have like search, like query, which is more a search. So still you could go and integrate your application with third-party services like TypeSense or Algolia, and then you can run those search queries on top of that. So Firebase doesn't provide you that. Then let's go and discuss about composite indexing. So if you want to run range queries on a given field, like let's say multiple range queries on a given field, then you don't have to create composite index for that. But if you want to run value compare query and range query on two different field, then you have to go and create index. So there are two ways you can do that. Either you can go and create the index from Firestore console, or you can just write your application, execute it, then it will give you a really nice error with a link. So you can click on that, you can go to the console, and it will automatically get created. But in Firestore, you are not allowed to have like multiple range queries. So this is very important. So when you are designing, you have to take this into mind. You don't have. So let's there is a special kind of operation is not equal. I recommend not to use this much as possible. The main reason is you will ended up getting a lot of document. Like if you run not equal query, that means the Firestore has to pick documents which like out of this like outside of this given set. So that's quite difficult query. And again, if you can't run range query with not equal. And again, if let's assume you don't have that field in your document, then those also will not be included in your output. So the whatever the like response, whatever the output is not accurate and not expected. So please like avoid not equal as much as possible. And I'll hand it over to you, Chamidu, back, discuss more about the guidelines and the design thinking, which is the crucial part of this presentation.
Yeah, thanks, Sukita. So basically now, I think Sukita and Samira mentioned that Firestore is a hierarchical has a hierarchical data structure, right? All the queries return documents from a single collection. We can use this hierarchy for filtering, right? Let's say, for example, now let's say you are doing restaurant reviews, right? Application, and then you have a collection called restaurants, right? So under a given restaurant, you can have a sub collection. So the advantage is, I think, from the couple of earlier slides, probably you got the idea that Firestore queries are not as flexible as SQL queries, right? You can't have a lot of conditions on different fields, right? So having this hierarchy is useful because of that, because then in the hierarchy itself, you filter on one dimension, right? So basically, now you can store your data in a sub collection, related data, if that data needs to grow, right? I think in the coming slides, we will come to see that there are certain limitations on document size, right? So storing items in a sub collection is a very useful approach when we want to query by parent, right? And then we can store, the other option is we can store data inside a map, inside the parent document itself, right? So again, remember that we don't have joins, right? So because of that, this approach might be useful if you want to query the parent documents by the field inside a map, right? So otherwise, if you have it in a sub collection, it's difficult to do that query. Then you have to, if you want to query items by a child document, you will have to run essentially two queries, right? Because Firestore is built in a way that they are billing for the number of reads and writes. So basically, I mean, it's not that expensive, but still, if your application has a lot of reads and writes, then you might have to be a bit conscious about these numbers, right? So now the third option, what if we store the data at a top level collection, right? So we have restaurants and then we have maybe reviews at a top level collection, right? Now that is useful if you want to query across all items. Let's say, for example, in the case that I mentioned, if you want to query across all the reviews for all the restaurants, you might have to do that, right? And the other is a hybrid between two approaches, right? Let's say, for example, you have, again, back to my example, right? Restaurants and reviews, right? So basically, now I think Sukita also mentioned earlier that when our data should be modeled according to access patterns. But let's say, for example, if you have a page that displays a brief about a restaurant, right? There you might have to display the top 3 reviews, right? So in that case, we can use, the last approach where we display some of the more relevant or more recent data inside a map, right, in the document, and then store the rest of it in a sub collection. Right? So those are like the approaches that you can take, right, with Firestore. So I think it's crucial for us to kind of like have a good understanding of these patterns, right, before we jump in and model our data, because there's a lot of ways to model data. Because if we model data in a relational database, there's actually one way, right? So you draw up your entity relationship diagram and you normalize the data down to at least the third normal form. So there's one set approach, you read the book and then you do it. But with NoSQL databases, Firestore, and as well as the NoSQL databases, you have to understand these approaches, the data modeling approaches, and select the appropriate one based on your use case. Can we go to the next slide, Samit? All right. So basically now the other approach, there are some other approaches as well. Sometimes you want to filter by keywords, right? A classic example is tagging them. If you have a blog post, you might tag them and you query by tags, right? So that if you want to do that, you can keep it in an array, right, inside the document, right? So, but if you want to query by multiple elements, then like if you use it in array, you can use array contents. But if you want to query by multiple elements, it's good to keep properties, all the properties inside a map, right? So, and the other thing is, now again, like Firestore is somewhat unique in the sense that it allows you to write applications without deploying server-side code. So that's actually a pretty good thing. Like you can write web applications, like single page apps without really having a server-side backend. Of course, sometimes when your application grows, you might have to use cloud functions or backend servers, but traditionally we all know that single page applications are not secure in terms of that you can't keep a secret inside this, right? But with Firestore, you can use the user's authentication to kind of like secure their data. So basically, this is about if you want to keep users access, you can keep it in the document itself and write security rules. So I think we have in the demonstration probably we'll show you how to do that, right? Now, if you want to keep private data, right? Sometimes anybody who has access to this data will be able to read that. But if you want to keep that authorization information, if you want to keep private data, it's advisable to keep it in a sub-collection, right? So basically, again, like if you want to model one-to-many or many-to-many relationships, you can keep IDs in an array. So for example, on the many side, you can have an array, right? Or you can use a snippet, right? So basically now the problem with using snippet is you have to always do resyncs, right? So for example, now if this happens even in MongoDB or any other database, if you keep denormalized data, what if the parent records change, right? Then you have to update all the other records, in a background process, or like in an event-driven manner. Okay. Anything to add to that, Sukita?
Yeah, I think yeah, that is fine. We are going to demonstrate cloud function to show like how we do the resync for these snippets. So that will be covered in the demo. So basically you covered everything.
Yeah. I guess we can move on.
Yeah, sure. So we are going into the data modeling. So basically we have some limits like the document limit 1 MB, that size, like that like if we take text, this is like a good size. We can store like a lot of fields there, but still we have to consider that it's not like relational database. So we have to download the entire document to the client side. So make sure that you keep like size as limited as possible in order to save the bandwidth and in order to give the maximum user experience. So make sure that you have like enough size, as I mentioned earlier. So there's like maximum field size in document that is like 20,000 or maybe 40,000. Now it might updated, but still may like the thing is, right, I'm not recommending going even into hundreds, because If we go into that like 100 level, that means like we have 100 indexes, 100 indexes created by Firestore, so it will be slow. So like stay in like 100 range as much as possible, or lesser is better. And again, queries are shallow. That's one rule. So we get only the document, not this associate sub collection. And queries find document in like single collection. We are not going to use group collection, like collection groups. It is still possible, and keep it as your last resort. Try to be in, querying in single collection to like maximize the performance. And yeah, so arrays behave differently. That's that we will see in demos. So I'll allow Samira to discuss the problem and directly go into the demo.
Thank you, Sukita. Let's discuss about the problem that we have come up with and the way that we have sorted it out with Firebase. So the problem that we thought of is to have a normal restaurant search or restaurant indexing application where users should be able to log in and register, and then they can see the restaurant that's available on the application. And when you navigate into a restaurant, you can see the menus that it offers and the reviews that the users has been given to the restaurant. And you can also add a review in there. Basically, these are the functions that we want to explain to you, but even if this is like few features that we have demonstrating to you, and under this is there are like a lot of things that we can explain to you how it works and how we have solved the problems that came with this application. Let me show you the relational ER diagram for a relational database. If you have to work on a relational database, this will be the ER diagram for that application. So here we have users. And a user will have an address. Which is one-to-one, and user can add many reviews for a restaurant. A restaurant will have many reviews. A restaurant will have many menus under single menu category or menu. There will be multiple menu items. For example, like restaurant offers dessert menu. Under dessert menu, you'll have ice cream and other sort of desserts. So this is the simple example that we thought of modeling into the NoSQL or Firebase, Firestore database. Let me go into it now. Okay, so this is the restaurant model that we defined for this application. We have the ID, name, description, and these types mean we can take it as cuisines. And the restaurant, we have an address here, phone number, these are the attributes of it. And this is the review model. Please look at this area. We have a key called restaurant, which contains a part of the restaurant object, not the whole object, but the object that we need to show some data without going into the restaurant object again and retrieving data, which will be inefficient. And we have the receiver information. Ideally, in a relational scenario, we will be having only the reviewer's ID, but in here we have reviewer's ID, name, and email, because these information that we'll be using on the application to showcase the users, showcase the review card. And then we have the rating there and the comment that's been given. And then the sorry, I'll go into the database and show you the menu. Okay, so this is the database that we have designed. As you can see, we have the users collection here, which contains user documents, email, and this is we're not using, but we have put it there: name, email, and favorites. And we have the restaurants here. Under the restaurant, you have a sub collection called menu. Under the menu, you have multiple menus for that menu categories, and under there we have the menu items. So as you can see, this is a hierarchical structure, and you may wondering, we have reviews collection here, and like I mentioned, we have the restaurant and review information. All the information we need to show this review as a card or as a view. So you may be wondering why we don't have this reviews under each restaurant. That is because mainly if we can have as a reviews as a sub collection for particular restaurant, but if we have that, we would not be able to generate this rating efficiently. That means that whenever user add a review, they are giving in a review value. For example, there are let's say there are 3 reviewers for a particular restaurant, and they're adding ratings. Whenever you do that, the calculation, the trigger that we have in there will be efficient if we have it in a separate collection. That's why the reviews are here. All right, so let's look at the demo application. Right. So this is our simple demo. As you can see, we have the list of restaurants here. We have the user information here. Let me just quickly sign out from here and let me register an account. So I've entered my credentials here, then I'm going to press register, which will register you and logs you into the application. When you click on a restaurant, you can see the menus that are there, and you can press user reviews. Yeah. So, and you can press here and then you read there. Yeah, it's quickly appeared. So this is basically without any backend, just on Firebase, using Firebase authentication, cloud functions, and Firestore as a database. We have used cloud function not as an API, but as database and authentication triggers, where whenever a user registered, the creating of the user document is happening through this trigger. So Peter will explain to you later in detail about that. So let me just go into the code and show you the nature of how we have implemented the Firestore and how easy it is. This is this SAMP application that we have, right, using Flutter. I mean, even with JavaScript, it's more or less the same. Let me just go into the authentication and show you the repository. Firebase authentication is really easy. So you have the authentication service from which is provided to you by Firebase, and you can either sign anonymously or you can have the create. You can create. Providers. You can do this. There are functions that you can create. You can register user just one line. Yeah. So after that, you will be authenticated. You will be issued a token, auth token, which you can use, which will be used to access Firebase. This is all through the SDK that Firebase provided. You don't have to do anything. And then you have restaurant, which is a collection, and this is like, again, this is like very simple queries, so more or less like an accessing API. But yeah, one thing I wanted to show you is that the real-time updates on Firestore. So I'll keep the list like this, and so that you can add a document from the database query to the restaurant. Then you'll see without doing anything that will appear here, which is we love about Firebase because it's what makes it so special. Um, okay, so the same document, so it has error, but see, without doing anything, it refreshed. So this is even we can have like this is just getting all the restaurants from the node, but you can have this as a search query. Like you can have like yeah, see, it updates really quickly. So yeah, that's what we have done. But the interesting things are happening behind the scene with database triggers and authentication. So Sukita is gonna showcase that to you. Over to you, Sukita.
Okay. Thank you, Samira. So let me share my screen and show you the function. Okay. So we know that Firestore provides us like really nice serverless interface. There are like two main components that we discussed earlier. So one is the Firebase rules, where you could change, like limit the access or provide like a security to your document. So that's very, very important, because when you try to access from client end directly to the database, then we need something like that. So that is the one component. And second most important component is triggers. So why we need triggers? So now all these communication, all these requests not going through any API. So there is limited intervention from our side. So there's no way we can intervene these requests, or we can do something based on this request, because it's not going through API layer as traditional application. So they have provided really nice way method to listen to these document changes or any things like user registration. So we can do or take some action, or we can put our business logic into the place based on these triggers. So I have like two functions created here. One function is here I am listening to the user creation. That's how user collection got generated here in this collection, and it just very simple function. And then I have a special function created for the average rate calculation. So let's say user come and change the review, because here you could see that review is in a top level collection, because we want to query it in a different way, like based on the user or based on the restaurant, or maybe based on the rate or something. We want to query the review. So because of that, we have placed it in the root level. So because of that, now I am listening that review collection. So whenever person come and add his review, or change the rate or something, then this function get triggered. So now it send me the change. So change mean the previous state and the current state of the document. So now I can check what changes has happened. So based on that, I can write my logic. If document changes from this state to this state, then what should I do? As an example, let's say here, if user has changed the rating, the previous rating and the current rating are two different, then I can go and calculate the rate again, and I can set it to the document. So that's very like simple thing, but still it's really powerful you to change your data according to different triggers. So this is very important. This is how we interact with or embed our application business logic based on different triggers, because we don't have API layer, right? So that's the main use case of cloud functions. There are like other use cases, like if you want to interact with external system. Let's say once user get created, you want to send an email using SendGrid, then what you can do, you can listen to that, you can write the integration here. So that's another use case. And here I want to talk a little bit about transactions. Let's assume now two individuals come and do the rate changing, and if you go and trigger this function concurrently, then our output could be inconsistent, or output could be wrong value. So because of that, we want to limit or we want to block the write until we complete this operation. So in order to do that, Firestore has provided something called run transactions. So inside that scope, whatever you do inside that scope are atomic, right? If that fails, then Firestore make sure that we roll back everything. And basically here what we have done, we create the transaction and we have the transaction object, and then we read the document we want to change, and then we do the calculation, and then we go and store the value. So there are like few rules we have to consider, and the one is like you have to do the read first, then apply the business logic, and then go and store the value. So that's the 3 main steps you have to take. And again, you have to make sure you don't have to do any side effect inside this block, because this block could run multiple times. Like, let's say fail, then it tries again. And so because of that, so you should not do any side effect inside this. And other main thing is, do not overload or overboard it. Don't try to put everything into transaction, and don't misuse the functionality. It will make your database slow. So there are two type of transaction Firestore supports. One is using optimized or optimistic, basically optimistic transactions. If you're using client SDK, then you are into optimistic. So if fail, it run again. But if you're in the server side, then it's like traditional SQL. It lock part of the database. So make sure that you don't overuse it or overboard. So that's about the transactions and cloud functions. So yeah, we can go back to the slides and see is there anything else we can discuss. Yeah, we discuss about the transactions, and then yeah, any questions?
So guys, we have the end of our presentation. And if you guys have any questions regarding Firebase and Firestore, Cloud Function, Firebase authentication, and how should we do the data mapping, please fire up your questions to the chat. We'll try to answer all. If not, we'll answer as much as we can. Let me check. Um, Naseem has a question. Can we use Firebase for large applications? So do you want to take it?
Yeah, it's possible. The only thing is, right, it based on your use case and the way you model your application. As I earlier mentioned, if you have like more reads than write, and then Firebase makes sure that the read performance of the query is not depends on the number of items. So if you are like talking about number the large application, mean the number of or the volume of data, then it's yeah, it's possible you to use for your application. But in certain use cases you might not be able to use. That depends on your use case. Like your application might be really complex, or you want to build a lot of complex logics on top of that. Then maybe you might go to Google Cloud Platform and start using queues or and a lot of features there. So that could be your your platform. So still it depends on your application. So if you need like more read heavy application like app related app driven platform, then yeah, definitely it's possible.
Okay. So Aruna is asking, since restaurant details are in multiple places, how can we handle update scenario to restaurant data? Example, updating the restaurant address.
Okay, so the thing is like how the first question is how often you go and update your address. Maybe like once or maybe never, right? So what you could do is you could go and write a cloud function listening to the main source, that is the restaurant, and then find all the places where these changes has happened and go and update them. Maybe you can use batch write to write all the places. So yeah, that is fine. And the other option is maybe you run schedule jobs. Maybe you run schedule job at at end of the day. You like find what are the changes has happened, and then you go and do the changes when there are no much load on the database or no much load on your platform. So yeah, that's completely possible.
Okay, so I'll take this one. No one is asking, is there a way to use an ORM framework with Firebase? Does it help to manage complex scenarios? So let me tell you this one. The main reason that we are trying to use Firebase is to get rid of the ORM nature of it, nature of the relational database. So there are, of course, there are frameworks or sort of like libraries that people have built for Firebase ORM, which I don't recommend to you, but there are. But I mean, if you are going for a object relational mapping or relational mapping approach, might as well go with the SQL or relational database one. It's if you are to go, if you're designing your application, database in a way that it can be retrieved in a hierarchical manner, if you think that will be ideal or that will be performant for your application, go with Firebase. Hope I answered your question on. Next, Nasim is asking, it looks like we need to revise our models frequently if the requirement get changed often. What is your advice, Suvita?
Okay, it again depends, right? So if you have like very frequent like model changes, that mean you don't have a good understanding about your domain. So and the other hand, your like your access patterns are not clear, right? So in this kind of scenario, still Firebase is a good option because it indexes all the fields. Okay, so then the only thing is then you have to write a lot of migration scripts when you're doing model changes. You have to run migration script to migrate all those things into again and again into collection. So because there is no hard schema in Firebase, so you still can have like versions where you have like old version set and new version set in same collection. Okay, so part of let's say your version 1 can still run on top of the in the same collection, so you don't have to like migrating from one database to another database, like in real in relational database. It's really hard because you have to go and change the schema, so your version 1 might not work on the version 2 of the table structure, right? So still my suggestion is go with Firebase, but definitely not with something like DynamoDB or Cassandra or that kind of databases which has like less number of indexing. Because if you take DynamoDB or Cassandra type of databases, you have partition key and only the sort key. So then you have to like really thorough with you, and you should have like really good understanding about the data model and the access pattern. So still, in this case, Firebase is your friend.
Thank you, Sukita. Hope that answers your question, Naseem. Is there anybody has any questions? It's your time. Let us know. We will try to answer it the best way we can. All right, sir, I think this is a wrap.
Cool. Okay, well, if you guys do have any more questions, please feel free to drop them into the chat box before we wrap up. I'm sure that our panelists will be able to take one or two more very quick questions. But in the event that there aren't any more, I'd like to thank everyone for joining the session today. Hope you guys learned a whole lot about Firestore and how you can improve your current practices. And of course, a big thank you to Sukita, Samira, and Chamindu for conducting today's session and for sharing their knowledge and expertise with our audience. So thank you guys for joining in, and thank you for being a part of Explorer Series episode 6. We have a lot more coming. We have future episodes of the Explorer Series, as well as other meetups and other sessions in the upcoming months. So do stay tuned. Check out our channels on Instagram and Facebook and LinkedIn for any updates. Thanks guys once again, and glad to have had you all. Have a good evening all. See you.